So hey everybody, my name is Xander. I'm a developer advocate at Arize AI. Today I'm really excited to be sharing with you a new open source library that we recently released called Phoenix. It's a library for ML observability and it runs in your notebook environment. Today we're going to be doing a pretty fun image classification workshop. It's going to be hands-on. You're going to get the chance to actually run a collab for yourself, try out Phoenix for yourself. We're really going to make everything as interactive as possible. I'm going to go, nice and slow, make sure that we're covering all the questions as we go. So yeah, I just want to say thanks for joining us. And again, going to be covering questions as we go. So feel free to drop those questions either in the chat or in the Q&A. I'm watching both over here. Going to periodically stop for questions to make sure everybody's on track. Awesome. So yeah, anybody there? Maybe I'll get a feel for like where are people at. And I'm curious also like how did you find out about Phoenix? Anybody? Yeah, would love to hear in the chat. I'm gonna go ahead and kick it off. David, we got the notebooks already in collab. I'm gonna share that link out momentarily. Yeah. So again, Phoenix is a tool for ML observability. We're going to start out with a high-level discussion of what is ML observability. Then we're going to go and switch gears a little bit and talk about Phoenix in particular and talk about what does ML observability look like in the context of Phoenix. After that, we're going to jump into the interactive portion of this workshop where you're actually going to get the chance to run Phoenix for yourself. Hey, Nidish, from Illinois. Awesome. Found out about Phoenix on LinkedIn. Thanks for joining. And then after that interactive portion of the workshop, we're going to reserve time for questions and answers. Really want to make sure that I reserve a lot of time in this workshop to get all the questions answered that we can. Awesome. So let's go ahead and kick it off. We're going to start out with a very high-level overview of what is ML observability. And at a very high level, ML observability has two parts, has two components: monitoring on the one hand and root cause analysis on the other hand. Your machine learning system is going to be observable if you've got both monitoring and root cause analysis. And what that means for monitoring is that you're able to detect issues when they happen in production. And what kind of issues are we talking about? We're talking about issues like data quality issues. So for example, if you are missing a feature in your pipeline by the time that you reach your model, the data is missing a feature. That would be an example of a data quality issue. Other kinds of issues are drift issues. If the distribution of your training data is different from the distribution of the data that you're seeing in production, that means that the data you're seeing in production has drifted from your training data. And we're actually going to see an example of this during the interactive portion of this workshop. And another kind of issue that we might want to be monitoring for is performance issues. So if you've got a classification model, like we're going to see today, and it has a poor accuracy in production, that would be a performance issue. If you have a credit card fraud detection model, and it's got a poor false negative rate in production, meaning that you're failing to catch a lot of cases of fraud, that would be another example of a performance issue. So again, monitoring just means that we're able to actually detect issues when they happen in production. But importantly, when we talk about ML observability is more than just monitoring. It's not enough to just know that something is going wrong in production. You also need to be able to quickly identify what's going wrong so that you can fix it. And that's what we call root cause analysis. And if that's a little bit abstract right now, by the end of this workshop, I'm hoping that it should be perfectly clear. And we're going to really work through an example of both the monitoring and root cause analysis in the context of Phoenix. So again, if there's one thing I just want you to take away from this whole workshop, it is this equation right here. What is ML observability? ML observability is monitoring plus root cause analysis. And importantly, monitoring all alone is not enough to make your machine learning system observable. Awesome. So any questions? I'll just stop there for a minute. Feel free to drop any questions in the Q&A, in the webinar chat as we go. Looks like we don't have any questions, so I'll keep going. Whoa, just spilled something. Sorry about that. Okay, that's all right. All right. So what does ML observability look like in the context of Phoenix? That's what we're going to cover next. This is an overview of Phoenix here on the right. This is actually what it looks like. And if there's a couple things that I want you to take away from this slide, it's these 3 bullet points. The first bullet point is that Phoenix, it runs in your notebook environment. It's going to run on whatever server is running your, whether it's Jupyter, whether you're running a local Jupyter server on your laptop, whether you're running a notebook in Colab, Phoenix is going to run alongside your notebook server. And as you can actually see in this picture, you can literally use Phoenix as an application within your notebook. The second thing that I want you to know about Phoenix is that it's going to do ML observability. So that just means it's going to allow you to monitor and detect the kinds of issues that we talked about on the previous slide. And it's also going to give you root cause analysis. It's going to help you figure out the issue. And that is actually what you're seeing here in this picture is actually ML observability in Phoenix. Up here at the top, as we're going to talk about, we're actually be able to detect drift. So this chart is actually drift of our production data relative to our training data over time. And you can see I'm actually able to detect that my production data is actually drifting in this particular time window. So this is monitoring. And then down here, as we're going to explain, what's going on down here is that we're immediately getting down and drilling down and pinpointing the root cause of the issue that's causing this drift that you're seeing in the chart at the top. So this is root cause analysis. This is helping you immediately pinpoint the issue that you're experiencing in production. Looks like I've got a couple of questions in the chat. Phoenix is the name of the, yeah, okay, David, we're good? Okay, no worries, all good. All right, so looks like we're good. That is Phoenix at a high level. Let's actually jump into the interactive portion of the workshop. I'm gonna get out of my slide deck real quick, and I'm going to jump over. Maggie, I think Maggie's already shared the link to the, yeah, it looks like Maggie already shared the link to the collab. So go ahead and scroll up in the chat and find that link. This is the link right here. Okay, Maggie shared it again. Awesome, thank you. And just to call out, you can actually access this notebook as well. It's right here in the tutorial section of our documentation under computer vision. And this is the exact link right here. Awesome. So go ahead and connect. I'm going to go ahead and connect. And for this particular notebook, you don't need a GPU. So I'm connecting. Looks like the Jupyter server has been provisioned. Let's go ahead and install Phoenix. That's going to take a minute. So in the meantime, I'm going to give you a sneak preview of the notebook and what are we trying to accomplish at a high level. So the name of this notebook is Active Learning for a Drifting Image Classification Model. So let's break that down. We're going to be dealing with inference data from an image classification model. The data that the model is going to be inferring upon is actually photographs of people performing various actions. And I'm going to show you some examples in a minute, but these are going to be photographs of people running, photographs of people eating, sitting, standing, riding bicycles, etc., performing various actions. And what the model is trying to do is it's trying to classify the action of the person in the photograph. As you can see here, the model's actually drifted. So we're actually going to be detecting an issue with this model in production. We're going to see that the distribution of the data is actually drifted. And the last part is active learning. So what is active learning? It just means that we're actually going to be pinpointing the exact examples that are causing the drift issue that we need to go back, get labels for, and fine tune our model on. So that at a high level is what we're going to be doing. And to start out, oh, looks like I'm having a scrolling issue. There we go. To start out, we're going to import some packages. So this is still running, but let's go ahead and execute some of these cells. We're going to actually download our data, and we're going to download our data into two pandas data frames. One is going to be a training data frame. One is going to be a production data frame. And we'll go ahead and view a couple of these rows. All right, looks like we're pretty close to catching up, so I'm just going to wait a moment. Is everybody managing to follow along so far? Cool, thumbs up, awesome. All right. So again, downloading training and production data for this image classification model, some of the rows or some of the columns of these data frames, they're going to be things like prediction IDs, prediction timestamps. Yeah, here we go. So the prediction ID here is, it's just a unique identifier for each row of the data frame. For each data point, we got a prediction timestamp. That's just the moment in time at which the inference was made by the model. We've got some URLs. These are URLs to a cloud storage asset that contains the actual image. We've got here an image vector. And what an image vector is, it's not the image itself. It is what is called an embedding vector for the image. So what that means is that we've just, from our model, we've taken this vector representation, which is just going to be the output from one of the later layers of our model. We've taken this vector representation that captures the semantic meaning of the images. And I think this idea, if you're not familiar with the notion of an embedding vector, will become clear in just a moment. And then we've got our predictions and ground truth over here. We've got our actual and predicted actions. That was the training data frame, and the production data frame, it's going to look exactly the same, except for our production data, we don't actually have ground truth. We don't have the actual action column. Awesome. Let's go ahead and take a look at some of the data. So now we're actually displaying a small sample of the training data. So here are the images. And again, these are images of people in photographs. We've got the ground truth label. So this person is drinking. And we've got the predicted label. This is the model prediction. In this case, the model made the correct prediction. The image is an image of someone drinking, and they are in fact drinking. Here's some more examples. This is a picture of people fighting. Again, the model is getting it right. Picture of people clapping. Again, the model is getting it right. More images of people fighting and sitting, and it looks like the model for this particular sample is getting all of the classifications correct. All right, so that is the data. Now we're going to move into the part where we actually launch Phoenix. To launch Phoenix, the first thing that we need to do is we need to tell Phoenix, what do the columns of my data frame mean? That's what this schema object is doing. It's basically saying, hey, we have a column in our data frame called prediction underscore timestamp, and that is the timestamp. We've got another column called predicted action, and that is the predicted label. We've got another column called actual action. That is the actual label. And this one is a little more complicated, but what this is doing is basically defining an embedding feature. So this is wrapping together the image URL right here and the actual embedding data itself contained in the image vector column right here. This right here is just a name that you get to choose. This is not a column of the data frame. This is a name that you as the user get to choose that's going to appear inside of the application. Cool. And we're gonna do that for both training and production, because if you remember, our training data frame and our production data frame were a little bit different. One of them was, the training data has this actual action column, but the production data does not. So the two schemas are actually slightly different. And here we're going to create a couple of Phoenix data sets that are going to wrap together the data frame right here, together with the schema that describes the data frame. And we're also going to give the data set a name, production on the one hand and training on the other. Those names are just going to appear inside of the application. Let's go ahead and launch Phoenix. All right, so at this point, Phoenix is actually launched, and you have two options for actually using the application. If you want, you can run the application inline inside of your notebook. So if you want to do that, go ahead and run this command right here, the px.activesession.view. That's going to let you use Phoenix inside of the notebook, like in that screenshot I showed you a couple minutes ago. But what I'm going to do is a little different. I want a little bit more real estate. So I'm actually going to open the application in a brand new tab. And when I do that, I'm going to actually be able to use my whole browser in order to use the application. All right, so let's just give that a moment. Awesome. Looks like it's showing up. And again, this was the image embedding that we defined a moment ago. We're also seeing here are predicted and actual values. We've got a couple of interesting metrics here. We've got things like the cardinality of each column. So that's like the number of predicted actions. You can see we have 15 different actions, percent empty, a couple of like data quality statistics, and what kind of data is it? In this case, these are categorical. David's got a question here. It says, how can I sort the clusters or filter based on prior understanding of my vector space? That's a great question, David. Yeah, I think we'll get there. No, you're good, David. I think we'll get there in just a moment. All right, so David is actually jumping right into where we're about to go next, which is this image embedding page. So what you're seeing here at the top, this is that screenshot I showed you a moment ago. What you're seeing at the top is, again, drift over time. It's the drift of our production embeddings relative to our training embeddings over time. And you can see that we started out with low drift. There was not much drift. And then sometime around this time frame, right in here, this time frame, something happened where the data that we're seeing in production drifted away from the data that the model was trained on. And as you might imagine, that can be like pretty problematic, because for image classification models in particular, a lot of the time they don't fare very well. They don't do very well when they're making predictions on data that they never saw during training. Right now, we're actually looking at this time window over here. Let's go ahead and jump down here though for the moment, and let's take a look at this point cloud. So to break this down, what you're seeing here is the production data in blue, the training data in purple, overlaid in the same space. What we've done here is we actually took those high dimensional embeddings, which were the outputs, or from the latter layers of your image classification model. We took those high dimensional embeddings and we reduced the dimension down to 3 dimensions. And that's what you're seeing right here. So let's actually make this more concrete. I'm going to go ahead and use the lasso, and I'm going to select this cloud of points right here. And I encourage you to do the same. I'll go ahead and pull up the pane, and these are the actual data points that you're seeing in this particular region of the point cloud. And again, you're seeing the production data points in blue and the training data points in purple. And if I just quickly glance through some of the pictures here, I can actually see that all of these pictures are examples of people cycling. They're photographs of people riding bicycles. All right, so that's pretty interesting. And that's actually really a good sign to us, because it means that we have good embeddings that are placing nearby images or similar images, semantically meaningful images, close together in the embedding space, because all of these images that are pictures of people cycling are getting put in the same region of the embedding space. And let's go ahead and check out some of these pictures over here. So I just circled this small little region, and it looks like these are pictures of people running. So again, a little bit more validation that we have good embeddings. We're seeing semantically meaningful regions of our embedding space. I'll just go ahead and do one more. Maybe let me rotate the point cloud, and I'll grab this little cluster out here. Let's check this one out. So this one looks like it's a cluster of people eating. Awesome. So that's a way of actually doing a quick sanity check to see, are my embeddings good? Is my model actually able to separate out the various classes that I care about into meaningful different regions of the embedding space? Nice little sanity check. But let's go back and let's put ourselves in the mindset of the person who's in charge of maintaining this image classification model in production. Imagine that you're this person who's maintaining the model, and you want to figure out, okay, I see up here in this chart that some kind of drift issue has happened. Like my production data has drifted from my training data. Let me figure out why that's happening, right? So again, this is the root cause analysis. Like up here, I'm monitoring, right? I'm seeing, oh, something has gone wrong. I've detected an issue. Now we're going to get down into the root cause analysis part of Phoenix, which is helping you identify exactly what went wrong. So when I clicked here on the Euclidean distance graph up here at the top, what I'm actually doing is now I'm only looking at production data from this window of time during which the drift was high. So before I was looking at production data from over here when the drift was actually low. Now I'm only looking at production data when the drift is high. And immediately, I'm going to rotate the point cloud around, but immediately you can actually notice something that is different about the point cloud now versus before. In particular, if I zoom in here, I'm going to just kind of move the point cloud around, and I want to just call your attention to this region of the point cloud. Can anybody, maybe notice something about this, right? Like it's all blue, but what does that mean, right? Like, why is that potentially a bad thing? No overlap, right? Yeah, so Nitish is getting it right there. There's no overlap. There's no overlap of the training and production data. This is all production data, right? So that just means that this is a region of your embedding space where your model is making predictions in production on data, the likes of which it never saw during training. And this is actually the exact reason that your model has drifted in production. It's because you're getting all of a sudden all of these production data points that are kind of like dragging the distribution away from the training distribution, which is the distribution here. So yeah, another quick sanity check, right? Like you can see, this is what your training distribution looks like. And then this is what your production distribution looks like. They look kind of different, right? There's this portion of the point cloud over here. It's present in production, not present in training. All right. And I could, if I wanted to, I could like find it, just like with the eye test and find these blue points and circle them using the lasso. I could do that. But yeah, David, hopefully this gets back to your question. We actually are able to do something a little bit more automatic than that, which is we're actually able to cluster these low dimensional points, the points in the point cloud, and we're able to sort them over here on the left. And the way that we're sorting them is by the kind of like the proportion of production versus training data. So you can see all of these clusters here at the top. This blue bar at the bottom here is all the way blue. And then as I go down, there's more and more purple, right? I think it's a little bug that we fixed recently, but there's more and more purple basically as you go down. And what that means is this first cluster is the problematic one, because this is the cluster where there's no overlap, as Nitish said. This is the cluster where it's all production data. So let's go ahead and click on this cluster. And let's check out some of the data points in this cluster. And immediately, you should notice like something immediately is different about the points in this cluster. In particular, all of the points in this cluster are grainy. They've had this noise added to them. This one actually looks black and white as well. And let's take another look at the second cluster. So again, the second cluster is also containing grainy images. And I can see this, here's a black and white image. And I'm also seeing another black and white image that's also had noise added to it, right? And let's click on the third cluster. And here I'm seeing, again, kind of more the same story, but actually a different story here. I'm seeing some blurry images. I'm seeing another blurry image here. I'm seeing a black and white and blurry image. This one is black and white. It's had noise added to it. And you can see, again, the reason that these clusters are being surfaced up is being potentially problematic is that these are clusters that are pure production data, right? All right, and I'm gonna, let's see, David, let's see, managed by exception, fine. Yeah, I think you got it, David. Yeah, so like, let me just check in, like, is that clear, like what's going on so far? Okay, I'm gonna take the silence in the chat as thumbs up. Oh, I'm seeing thumbs up. Awesome. Thanks. Lots of thumbs up, lots of party. Okay, so I think if we're clear so far, the next step, right, is like, let's just recap where we are right now. Where we are right now is we managed to detect drift. We managed to automatically pinpoint the exact data points in production that are causing the drift. We managed to inspect those data points. And now we have a hypothesis about what is causing the drift in production. Namely, we think that our models drifted because we're seeing images in production that are grainy, that have noise, and that are black and white, and that are blurry, that we never trained on. That is the story we've got so far. So now that we've monitored our model and detected an issue and found the root cause of the issue, we can now, fix the issue, right? So the next step is let's actually export these clusters. What I did was I clicked on this export button over here, and I encourage you to do the same. What that does is it's actually going to save off all of this data inside of this cluster. It's saving it. And now what I can do is I can come back to my notebook environment, and I'm going to scroll all the way down to the bottom, and I'm actually going to run this cell. This is just calling sessions.export. And what this is right here is actually that exact cluster of data that I saved off. And now I've loaded it back into my notebook. And I can actually look at a few examples here. So these should look familiar. These are the exact examples from that cluster that we were just looking at inside of the application. But now I've actually got the exact data that I need in order to fine-tune my model. So as a next actionable step, what I can do is export those problematic clusters of data, label them, and fine-tune my model in order to improve the performance of my model in production on this kind of data. Okay, let me pause there and see, getting a couple questions here. Okay, so David, David, this is an interesting point, right? Like scale. Let me see. David's asking, at scale, maybe this wouldn't work. Yeah. So I think that's a fantastic question. I'm actually really happy that you asked that. I'm gonna get to that in just a minute. So David's asking about scale, like how could you scale this? It seems like this wouldn't scale very well. And then we got another question, how to get an image vector, any specific format used for input parameters in, oh, okay, that's a great question. So we got another question around like how to get an image vector. And then we got another question here. What if the model starts picking up on graininess or blurriness as a feature of the target? What if the model starts picking up on as a feature of the target? I see. Okay, so Jugo, that's a good question. I'm not quite sure I understand that one, but I'm going to go through these one by one. So first question here was from David for scale. That's a great point, right? Like you can't just run UMAP on an infinite scale. You actually can run it relatively high number of points. And I think that's actually an area that we're actively working on. So I think one idea there would be you sample your points. You do this approach with UMAP. You get a sample of the kinds of points that have drifted, and then you are able to, if you have like an index of your all your data, so you have all your images, like a huge number of images, you take that sample and then you go back to your index and you do a similarity search for similar images in your index, and then you pull all of that data. So I don't know if that was clear, David. That's like kind of like a little foreshadowing of some of the ideas that we have around scaling this to a larger extent. The next question I think was around generating image vectors. Next question was around generating. Thanks, David. Appreciate the questions. Next question was around generating image vectors. So that's a really good question. I would actually refer you to this page in our documentation. Let me see real quick. We've got a whole section right here in our documentation around different ways to generate embeddings. There's a lot of ways of generating embeddings. I mentioned one, which is, it's this section right here. So how to generate your own embeddings. I'm gonna drop this in the chat. But long story short, there's a lot of ways of generating embedding vectors. There's many different ways. That in part is up to you as the data science practitioner. If you have some kind of specialized knowledge or specialized understanding of your data, and you think that this particular way of generating embedding vectors is going to be the most appropriate for your data, then by all means use that. I'd also point out we've got this right here, which is a nice little tool that will actually help you generate embeddings with our SDK. So I'll drop those two resources in the chat. Next question is, the next question I think was what do I feed as a feature vector for segmentation models? Okay, so yeah, that's a great question, Sushil. Feature vector for segmentation models. You know, we don't currently support image segmentation models. If that's a great question. And like, if that's something that you're actively trying to support, definitely hit us up, let us know. We've had like a request for that feature. So it is on our radar. In terms of like what feature vector to use for image segmentation models, I'm not actually sure off the top of my head because we haven't actually played around with that enough. So I think I'm gonna have to say, let us know if you really want that. And we got to think about that one a little bit. And then I think there was one more question from Jugal, which was around, actually, I'm not seeing the question anymore. All right, I think I lost that question. And I'm seeing one more question. Is my understanding correct that Phoenix would work with anything that can be represented as an embedding like text or even a chemical structure, thinking of QSAR models? Okay, I'm not sure what a QSAR model is, but the answer to the question, Alex, is yes. Phoenix works anytime that you can represent your data using an embedding vector. And actually, we're going to be running a series of these workshops on different use cases. So today we talked about image classification, but if you come to our documentation, you can see, where's our documentation? You can see some of the tutorials over here. Some of the tutorials that we have out are for NLP. So as you said, like you can represent a piece of text with a vector. We have examples for LLMs. We've actually, interestingly enough, got an example where you can actually represent tabular data using embeddings. So yes, answer to your question, Alex, anytime you can represent your data with an embedding, you could use Phoenix. And let's see, here's Jugal's question. What if the model starts picking up on graininess, blurriness as a feature of the target? Yeah, Jugal, maybe you could expand or elaborate on that one. I'm not quite sure what you have in mind there. All right, and then what are other issues apart from drift that can be observed using Phoenix? Yeah, that's a great question. So really, we've got, like, I would encourage you to just check out these tutorial sections. Again, we're building Phoenix to be able to monitor the kinds of issues that I mentioned before, which are data quality issues, which are drift issues like you saw today, and performance issues. So I would just check out some of these and stay tuned, because that's something we're actively building. We're still early days, but we're actively building towards supporting, detecting those three classes of issues. All right. Awesome. Looks like that was all the questions. Jugal, I'm going to follow up with you individually just to see if I can actually answer your question. Yeah, as a little bit of a last plug, let me see. Oh yeah, by the way, this is our contact info. If you like what you saw, go ahead and check out the repo, leave us a star. We really would appreciate that. We've also got our Arize AI Slack community going, and we've got the Phoenix support channel. We're really responsive in there. So if you run into any issues, I'm in there all the time. Our team is in there. We're happy to answer issues, get you unblocked. This is my personal email. Go ahead and email if you have any questions. Yes, Sushil, the recording will be available online. One last pitch. We've also got, Maggie, what is the date on the AnyScale workshop?
It is June 1st from 5:30 to 8.
Awesome. Awesome. June 1st, 5:30 to 8. We're doing a joint workshop with one of our partners, AnyScale. And the workshop is going to be on fine-tuning and analyzing LLMs. So in the first part of the workshop, we're going to use an open source tool called Ray to do distributed training on an LLM, distributed fine-tuning on an LLM. And then in the second part of the workshop, we're actually going to use Phoenix to visualize the data. So we'd love to have you there if you're in the area. And I think we'll have some online resources available at some point for that as well. Awesome. If there's no other questions, thank you so much. We ran a couple minutes over, but really appreciated the questions and the participation, everybody. Awesome. Thanks.